G'day everyone, we're back here with a topic that I think is a relatively simple one if you understand what you're doing, and that's related rates. Related rates is exactly as it sounds. When we take the derivative of something, we're relating the rate of change of one to something else. So dv dt, which you should know as acceleration, is the rate of change of velocity with respect to time. Well, in this part of the course, we're using many different rates and putting them together effectively using the chain rule. Okay, so let's put this in context. It's always easier to see it and then link back to the idea of chain rule and the idea of related rates. So put them aside for a minute. Let's get into a question. This particular one says we've got an oil spill. Now you may recognise that if you spill oil on the ground, it'll pile up to a certain height, but then it starts spreading outwards. As you add more oil to it, it spreads out and keeps a fairly constant height. So we're assuming that the height is 5 centimetres. Now in practice, it might come across at the edge here. Let's not worry about that. The questions give you a specified height. Now I can write a formula like this for that area, or for that volume. Pi r squared is the circle area times the height. Now, importantly, this here is not a variable because we know what that is. It's just a number. So we don't need to do anything with that in terms of our differentiation. Okay? Now I can substitute that in as well, but I'm just going to leave it there for the minute. Now if I want to work the derivative of this, remembering that r is the only variable there, I'm going to get dv dr. So if I work that for us, aren't we going to get dv dr, and won't that be power out the front 2 pi r h, remembering that's a constant. Okay? Now the question for this one told me that the rate of volume going in with respect to time is 5 meters cubed per minute. That's how much oil is spilling into that shape. So this is volume with relationship to time, whereas from here I can get volume with relationship to radius. But neither of those are what I want. What I want is the radius with respect to the time. I want to know how quickly this thing is growing, not how much is going in, not the link of volume to radius, but how quickly is it expanding with respect to time. So I want dr dt. And the question says find dr dt when the radius is 20. Because remember, the rate of change of the radius will change with respect to when you are talking about. Think about this. If the oil spill is really small, and I'm putting in this amount per unit time, per minute, then it's probably going to be growing quite quickly because it started small. But once it gets to this size, and I'm still adding the same amount per minute, the rate of increase of radius will slow. So it'll start very quick, and then slow and keep slowing, and effectively forever, it will always be increasing because I'm always adding more, but the rate at which the radius is increasing continually slows. Okay? So hopefully that makes sense. If it doesn't, kind of play it out in your mind of how oil would work if you kept adding the same amount to it and look at the radius. Right, now, a couple of things we've got to be careful about here. Be careful about the units that they give you various measurements in. Okay? Related rates will only work if the units are the same. So this was in meters cubed, this was in centimeters. So I would probably change this to 0.05 meters. That's the easier conversion to do. I could have changed this as well into centimeters cubed, but it's going to be a big crazy number. This is going to be easier. Right, what do we got to do? Well, here we are with our related rates idea. I've started it out there a little bit. So this is what I want, dr dt. That's what I want to finish up with. But I know that I've got to start somewhere here. Now, see how I've already put that guy there and that guy there. Because remember, with our chain rule, they have to be over there, don't they? So now I've got to figure out, well, what's going to go in these two? Well, it's actually got to be the same thing. Because whatever goes in there, I kind of want to be able to theoretically cancel out, don't I? And when you look back at the question, I'm sure you can spot it. Volume is the thing that fits here and fits here. So I reckon that's going to be dr dv times dv dt. Because I've got dv dt here, and while I don't have dr dt, I just need to flip it upside down and I'll have dr dt. So it's dr dv. So dr dv flipped upside down, isn't that going to be 1 over 2 pi rh? And isn't dv dt going to be 5? Now from there, it really is just going to fall right on out for us. This guy's going to go in there for h, this guy's going to go in there for r. The rest, it's just a bit of number crunching. So what are we going to have? 5 over 2 times pi times, what was r? 0.05 times 20. Now, I see the 5 on the top line and the 0.05. Well, what do we got? If I go 1, 2, that's the same as multiplying by 100 on the bottom line. So wouldn't I have to multiply by 100 on the top line to get rid of all of that, to make it a little easier? And then once I see that, 5 and 5, so really 100 will cancel this guy out here. You might do it a different way and that's okay. The 100 and the 20 there, this will bring it back to a 5. So I reckon it's going to be 5 over 2 pi, whatever that ends up being, I don't really care. And remember, this is dr dt. So the units that I'm going to need on there is the units of the radius, which was in meters, and the units of the time, which was in minutes. So I reckon this will be meters per minute. So the rate of change of the radius with respect to the time, when I have a circular, or a, really it's conical, it's a cylindrical, but circular shape, with 5 meters cubed per minute going into the oil spill. At the moment that the oil spill is 20 meter radius, the rate of increase of the radius with respect to time will be 5 over 2 pi. Decimalize that if you want to. Hopefully you see where we're going here. The numbers aren't so important here, but the idea is to use the chain rule to link things together that I can't in any other way link together, but I can work out my derivatives and get them together, get the right things in. Key points are, see where you're going. See what you mean, see where you're going before you even start working here, and see the units. Get the units right. That can derail many a question if you don't have the units right. Hopefully this video has helped. I'm going to do another one in a minute with the style of question where you're actually walking along with a shadow behind you. That's a common question as well. So this is a common one, the shadow one's a common one, there's a couple of other ones. Make sure you know how to do them and then they shouldn't trouble you at all. Hope this helps you guys. Catch you later.